Let's go ahead and learn about magnetic flux, which is one of the most important topics you need to know about when it comes to electromagnetic induction. So, imagine these red lines as a bunch of lines that represent the magnetic field lines of a magnetic field. If I were to place a metal coil in a fashion that is perpendicular to these field lines, what would happen is that this coil, which is perpendicular to the magnetic field line, has a bunch of magnetic fields that are going through it. The total number of these magnetic field lines that go through would be called the magnetic flux. So magnetic flux is simply the total number of field lines. It is denoted by the letter phi, which is drawn like that. You can calculate the magnetic flux simply by multiplying the component of the magnetic field, which is perpendicular, by the area through which the coil exists. I mean, whatever the area of the coil is. The unit of the magnetic flux is Webers. Magnetic field intensity obviously is measured in Teslas, and the area is measured in meters square. Now, there's something you've got to be very careful about. When I said that the magnetic flux is simply the magnetic field that is perpendicular to the area of the coil, there's a tiny detail that needs to be added into this whole equation. So that means that if you want to calculate the flux, you have to find the magnetic field times by the sinus of theta times by the area. So what exactly does that mean? So that means that there is an angle between the magnetic field lines and the coil, and you can call this angle theta. So the component of the magnetic field that is going through the coil should be measured for cases where the magnetic field lines are entering the coil at an angle. In fact, this is used when the magnetic field lines are going through at an angle. Now, there's a couple of special cases. If the magnetic field line is going through at a perpendicular angle, which is 90, then you have maximum flux. So if theta is 90 degrees, then phi is equal to b sinus of 90, which is 1 times the area. So magnetic flux is simply b times a. But if the magnetic field lines are parallel to the coil, like in the scenario that I'm about to draw, so imagine these are the magnetic field lines, and this is the coil. It's placed in such a way where no field lines are able to enter it. So it's parallel with the direction of the magnetic field lines, and as a result, the angle between them is simply 0. And since theta is 0, we know that because of that, the magnetic flux is going to be B times the sinus of 0 times A. So magnetic flux is going to be equal to sinus of 0, which is 0, and as a result, the flux is equal to 0. So if the magnetic field lines are parallel to the coil, then we have no magnetic flux because no field lines are able to enter the coil. Now let's go ahead and do a problem. Example number 1. Let's say we have a 20 by 20 centimeter square, and we're supposed to calculate the magnetic flux through the square. So calculate the flux through a 20 centimeter by 20 centimeter square. And let's assume that the magnitude of the magnetic field through which the field lines are created is about 6 megateslas. Now, imagine that in one scenario, the magnetic field lines are going through at an angle of 40 degrees, let's say 45 degrees. And in another scenario, the magnetic field lines are going at an angle of 90 degrees. Now, the area in this question is simply going to be 20 times 20, which is going to be about 400 centimeters square. 400 centimeters square has to then be converted into meters. You could just do that from the beginning. You could simply say that 20 centimeters is just 0.2 meters. So 0.2 times 0.2 is 0.04 meters squared. Now let me just check that. Yeah. Now, in order to find out the flux, you just have to say phi is equal to the magnetic field intensity, which is 6 megateslas. Mega stands for 10 to the power of 6. So 6 times 10 to the power of 6 times 0.04, because we're supposed to say that phi is b sinus of theta times area. So far we're multiplying the magnetic field by the area and then multiply it by the sinus of the given angle, which is 45 degrees. So phi is simply going to be 6 times 10 to the power of 6 times 0.04 times sinus of 45 degrees. The answer is going to be 169,705 Webers. And this would be the flux created with a magnetic field that is given. That's quite a large flux because of the intensity of the magnetic field. Now, if the theta, or the angle between the field lines and the coil, is 90, then we can assume we have maximum flux, and maximum flux means we just have to multiply the magnetic field by the area. So phi max is going to be equal to 6 times 10 to the power of 6, or we could just keep the mega. We can just say 6 times 10 to the power of 6 times by the area. So we can say 6 times 0.04, that's 0.24. 0.24 times 10 to the power of 6. We can say it's 0.24 megawebers, or simply phi is equal to 240,000 Webers. Let's go ahead and take a look at another question now. Now, sometimes we can use the equation of the maximum flux density to actually find out the magnetic field intensity as well. So just keep in mind that if phi is equal to b times a, if I were to divide both sides by the area, then I can actually get the equation for magnetic field density, which is the magnetic flux divided by the area. This can be useful in certain situations, so you can note it down. Now, let's imagine I have a magnetic field with a magnetic flux density of 20 milliteslas this time, with a area of 10 to the power of negative 4 meters and a magnetic field intensity of 10 milliteslas. Milli stands for 10 to the power of negative 3. So how much is the flux if the theta, or the angle between the field lines and the coil, is 0? Right off the bat, I know that the magnetic flux is just the magnetic field times the sinus of theta, so the perpendicular component of the magnetic field, times by the area. So phi is going to be 10 milliteslas times the sinus of 0 times by the area, 10 to the power of negative 4. And we know, since sinus of 0 is 0, this indicates the fact that the magnetic field is perpendicular to the coil, and as a result, the flux is simply 0. Thank you for watching.